Hello there, my name is Richard Kay. I'm CEO for Champion Ball Bearing out of Palm Springs, California. The following discussion and testing applies to bicycles, skateboards, and roller skates. Do you want to finish more than 100 yards ahead in a 100-mile bicycle race by simply changing the ball bearings in your hub? Sounds too good to be true, but it's possible with today's new ball bearing technology. Available for more than 100 years, the ball bearing has recently benefited from several major technological innovations and material changes. As an engineer and manufacturer of ball bearing systems for industrial use, I was naturally interested in the possibilities for the bicycle. Part of this new bearing technology uses fiberglass Teflon seals for bearings that offer numerous advantages over rubber or metal seals, including a lower coefficient of friction, excellent lifespan, and when applied correctly, significantly reduced bearing resistive torque and achieved increased sealability. Solid film lubrication in the form of ion deposition uses vacuum and an inert gas plasma with high voltage to coat bearing surfaces. It produces an ultra-clean bearing surface because of a argon ion bombardment just prior to applying a thin lubricant coating. Excellent adhesion is obtained by driving the vaporized atoms into the ball bearing metal surface by intermolecular adhesion. This is a non-line of sight process. It covers components with complex geometry. Of the materials tested, tungsten disulfide proved to provide the lowest torque. A preliminary bench test showed that by simply changing the seal material and configuration in just the front and rear hubs, a significant performance increase could be realized, and that something so random as a speck of dust could possibly decide the outcome of a 100-mile bicycle race. An energy analysis equation presented by Chester Kyle in the August 1987 Bike Tech magazine shows how. The question we were anxious to answer was, what effect do a variety of parameters have on bearing torque, specifically seal material and design, type of ball retainer, and lubrication? All that remained was to accurately measure the bearing torque. Repeatable results were obtained slightly more than a year ago using a rotating disc of known mass and inertia and a chopper disc attached to the rotating disc passing through a stationary GE H21A2 light emitting diode. Once every revolution, the chopper disc breaks a light beam in the light emitting diode. The signal, after passing through a Metrobyte P10-12 digital board, provided a graph of torque versus RPM. The input signal, a first derivative of RPM, was processed with an IBM PC through a series of computations written in the programming language Pascal. Once the test flywheel was taken up to speed, 400 RPM, and the external driver disengaged, the computer accurately noted the change in RPM and printed out the RPM versus torque data for the test apparatus. The torque calculations were from the equation T equals I alpha, and the RPM taken between calculations. Torque values were recorded at 25 RPM intervals from 400 down to 200 RPM. The calculations suggested an inertia mass of 17.36 inch-pounds per second squared, with a weight of 105 pounds mass. The idea of a rotating mass and a partial vacuum offered a fair compromise between variations in lubrication characteristics in a vacuum and test repeatability. This was because of daily barometric pressure fluctuations and associated windage and friction considerations. Therefore, as a result of size restrictions, the inside diameter of the available vacuum chamber was 20 inches, the inertial load could be only 1/4 of the load of a bicycle and rider. But with a radial load of 105 pounds and a rotational speed of 16 to 32 miles per hour, the most significant performance variables could be approximated. The drive mechanism consisted of a DC motor mounted on a half-inch diameter linear bearings, while the motor was engaged and disengaged by a mechanical feed-through. The bearings were mounted in 4 1-inch diameter vertical supports, 3 of which are visible in the photo. Inside the vacuum was 25 inches of mercury, plus or minus 1/4 of an inch. For comparative purposes, the following configurations were tested. The Sun Tour bicycle hub was tested with 3 types of bearing systems. Basically, that's it.